All right. So, in the previous lecture we sort of introduced the concept of 3D wing versus 2D wing. So, we know airfoil is there, and then what exactly airfoil implies and how tip vortex actually brings in this 3-dimensional effect of flow, and that actually one can. So, this is the visualization of that. I mean what exactly the tip vortex really mean, and what actually it mathematically does to the airflow. So, this is something which happens pretty close to the wing. I mean I believe I have earlier drawn this kind of diagram where, I mean if I look at half wing, this is my half wing, my lift distribution, sorry, I should have drawn it all the way here. So, the lift distribution would look somewhat like this, which means it is at the near the tip it will go down to 0, and that is actually done by this tip vortex effect. So, what tip vortex does is that it actually induces this downward component. So, one can look this as in two different ways. One is that, I mean if I draw my normal airfoil, and let us say this is my free stream, and then this happens to be my angle of attack, right. Now, because of this presence of tip vortex which induces this downward component of velocity w. So, what happens, this particular line would now get tilted. So, what is happening, there is a w added to this. So, this is my v infinity, my free stream velocity, and now this small w has appeared because of the presence of tip vortex. So, what happens now, this tilts my direction of flow. So, I can do vector addition. I hope all of you are familiar with normal vector addition. So, if I take any vector a and b, my resultant would be like that, right. So, this is my a vector, this is my b vector, then this is, I can say c vector. So, c would be equal to a plus b, right. This is your normal vector addition. So, that is what is happening here. So, now I have a new resultant, this v, which is combination of these two things, but now importantly what it is doing is that it is actually decreasing my angle of attack with this small angle, right, because it is flat, but now I mean I have actually, because of this w, it is actually coming about some angle like that. So, you see now this is my new reduced angle of attack. So, right at the tip, exactly at the tip, this angle of attack will go to 0 basically, but everywhere else it will be having some small finite effect, and this effect you can see is closer to the tip. So, whenever we want to design an aerial vehicle which actually we expect it to have better aerodynamic characteristic or higher L by d, because finally that is our aim, I would want to have a wing which has less and less of 3D effect. So, can any of you tell me, I mean what can be done to reduce this 3D effect? A winglet is fine, but if I yes, winglet is one way where I actually have a something added to the tip, I modify my tip. If I do not modify my tip, if I have a normal design, what can I do? Because winglet is not very straightforward thing. I mean you may think, I mean I have to just curve something up. It is a very I would say focused and niche thing. If you do not design winglet properly, it would actually make it worse for you. So, instead of modifying tip vortex, you may end up making it worse. So, the winglet design is a very scientific thing which you have to do in a very careful manner with proper studies and everything, and it may work in some conditions, it may not work in some other conditions. So, it is a tricky thing to do. So, if I just want to, if you do not go there and I just want to design something which should have higher L by d, which means I should have lesser of 3D effect, because what this is doing is that this is reducing my lift or increasing my drag, right. So, this decrease in angle of attack would mean two things, let us understand. One is of course, what is the direction of lift with respect to my free stream velocity? Perpendicular, right. Okay. So, if this is my flow, so initially my flow was this direction. So, my lift force would be, originally it was like this, right, and my drag force was in this direction, agree. Now, because of this induced effect, my angle of attack has decreased. So, my flow is now coming about this direction. What does this mean? That my lift will tilt backwards. All of you can see that. Let me draw it again probably more clearly. So, this is my airfoil, this is my original direction, and now my direction is in this, right. This is my direction of flow, which means my lift will also tilt backwards, right. Earlier my lift was vertical because my flow was vertical, horizontal rather. So, this tilted back lift means there is a component of lift which is going in direction of drag, right. So, I can easily resolve this guy into this and say L prime and some well L d. So, you are getting my point. So, basically this induced velocity is doing two things. One is it is decreasing the angle of attack near the tip, which I can see in this picture, right. I can see in this picture that my lift near the tip is going to come down. And second thing it is doing is that it is tilting my lift vector backwards, and as a consequence you are now incurring some additional drag because of the lift. So, this we can call as lift induced drag or simply induced drag, yeah. That is the thing, right. So, this results in decrease in angle of attack, and it causes increase in drag called induced drag. It alters flow field about wing to change surface pressure distributions in direction of increased drag. Local relative wind is canted downwards, lift vector is tilted backwards. So, my wind is canted downwards, okay. So, which means I mean it is decreasing my angle of attack, and the lift vector itself is tilted back, and a component of force parallel to V infinity would now appear. So, this is source of induced drag, and the another way of looking at this induced drag part is that certain amount of energy is leaving through this wing tip vortices. So, whatever energy is being created by acceleration of flow over the wing, see flow is coming, it has some kinetic energy half m dot v square or something. So, that I mean once it goes over the airfoil, it undergoes some acceleration deceleration, and because of which my pressure distribution happens. But now because of the stiff vortex, some of this energy change done by the wing is getting lost and it is not getting accounted for. So, finally, if you think of I mean friction, friction creates similar kind of loss, okay. So, energy is lost there, yeah. So, same way this vorticity, the tip vortex is also creating some kind of loss which can be thought of as certain amount of rotational kinetic energy getting lost to the flow, yeah. So, some energy is lost. So, this is same thing we are trying to understand or reason it from different angles. So, this actually is a important component of your drag, and that is what one tries to cater to. So, coming back to my original question, which was that what do I do to improve my 2D behavior and reduce my 3D behavior other than winglet part. Okay, one thing is I can modify my plan form, make it tapered or something. So that I mean as I go close to the end of the wing, my lift generation and the pressure difference between top and bottom will come down a little bit. But tapering is also a tricky thing. I mean my manufacturing of wing becomes more tricky.
On tip we can use instead of camber airfoil we can use symmetric airfoil kinds of.
Yeah, fine. So, I can try to but even then see what, because you are always going to be at some angle of attack, you cannot make it at a 0 angle of attack, right. So, and this will require I mean again a modification of my airfoil choice. So, we are making, when we are making small UAVs, we are not going to make very complicated wings, very simple things. So, I am asking about the simplest possible way to enhance my 2D effect and reduce my 3D effect.
Just blades at the end of the wing.
No, but that is what we are winglet. Okay. So, we are saying we are not going to do any of that because it is a tricky thing to do, it is not easy. Twist is a different thing altogether. I mean that also is you will not have in normal small UAV wings, okay. You will not twist them. Exactly, the simplest possible thing, right. If I make my wing very long, okay, this part will become smaller and smaller. So, overall contribution of this tip vortex effect would be far less. Okay. So, if I make my very long and slender. So, imagine this wing versus this wing, right. So, they may have similar areas, but this guy will have better L by D because my induced drag will be less. I can just say that blindly, going with the same airfoil and same other things, while this guy having shorter wing will have poorer L by D because now I mean lot of area will be influenced by this tip vortex. So, that is the trick people use when they make gliders. Okay. So, if you go to our flight lab and you will see couple of gliders there, and you will notice that compared to a Cessna airplane which is sitting there, which is 6 seated, my glider is only 2 seated including pilot and the passenger or co-pilot. Wingspans are almost similar. So, how does that actually compare? So, if you look at Cessna's L by D, okay, so we are now talking about lift to drag ratio, okay, and this is the key determining factor for my performance most of the time. Okay. Another parameter will also come in, we will come to that later actually, but this is the most defining parameter which governs my design all the time. Moment you look at a UAV, you would want to know what is L by D of this. Okay. If it has good L by D, you can assure that I mean it will have good performance characteristic and it is going to give you the most optimal performance. So, manned aerial vehicles or full scale aerial vehicles would typically have L by D of the order of 10 to 15, okay, 10 to 15. So, my Cessna would be somewhere in between this 12, 13, 14 maybe, okay. And the glider which we have, Sinus pipistrel glider, that actually claims to have L by D of 23. Okay. So, glider, you can note down here, glider has L by D, claimed L by 23. Okay. Why does it matter to me as a UAV designer or a UAV engineer? What application would be there where I would want this kind of high L by D and so okay. So, let us take one step back and before I ask you this more difficult question, let us try to understand and answer a simpler question, okay, which is what is the difference between a glider and an airplane?
Sir, a glider can go to the air and then if we shut up the engine, it can still glide on a
No, an airplane can also glide. Okay. So, if I look at any normal general aviation airplane, okay, small airplane like what we have, it is statically stable. So, if it is unpowered, it will be still able to glide. Every airplane is typically capable of gliding without requiring any autopilot or anything. As long as your controls are active and you can move the controls, you can glide easily, you can maneuver also. But what is the difference between a glider and an airplane?
So, they can still glide, but because of high L by D, glider can glide up to high endurance and long distance.
Right. So, your L by D directly influences your sink rate, okay, or your glide angle, at what angle it will actually glide down. So, if my L by D is higher, my this angle will become very shallow, which means I will sink very slowly. So, it is like I will keep floating in air for very long durations, and this is something which becomes very important for design of a particular class of UAVs. Are you familiar with this HAPS term? It stands for pseudo satellites, right. What are they supposed to be?
They roam around in the stratosphere.
Yeah, so these are aircrafts which would be flying at almost 50 kilometer altitude, 40 to 50 kilometer altitude. Your normal commuter airplanes do not even fly there actually. Commuter airplanes fly at 10 kilometer, 10 to 11 kilometer, 40,000 feet, 35,000 feet and thereabout. Here we will be flying at 40 kilometer or above, okay. And the idea is that I mean instead of launching a satellite which is more expensive and putting a payload on that is more difficult, I can actually put similar payload on a UAV which will be flying at this kind of stratospheric height at 40 kilometer odd and fly continuously for 3 months, at least 3 to 4 months time, okay. And then I mean you can bring it back and maybe replace it with another similar craft So, this will keep doing station keeping. You can even move it from one location to another location, because it is a flying vehicle. So, it can keep loitering in a circle, and then I want it to move to some other location, I can take it somewhere else. Okay. And idea is that, I mean, with this I can use it as a spy satellite basically. So, with appropriate payloads I can pretty much see my entire neighborhood, right. So, because at such heights, I mean you can see very large areas, right, if you have powerful enough payloads. So, this kind of crafts, I mean, there are 2-3 approaches being explored. One is your lighter than air kind of system, which would be based on your helium, hydrogen based balloons, airships for that matter, but that is a very tricky business. They look very attractive and simple, but they are very messy and difficult to handle because of their bulk. So, better option which is being explored, and now I mean significant work has been achieved abroad, and in India also there is a lot of work going on, is to build solar powered UAVs. So, solar powered UAV means, I mean, you will during the entire daytime you will keep generating energy to keep your batteries fully charged, and enough to make you climb also. So, you have enough additional power which allows you to climb up. So, that at night time there is no power. So, whatever power you have stored, you will use it to sort of power your payload and peripherals and glide. And that is where you will want to do very shallow glide. So, these solar powered UAVs, their wing spans run in hundreds of meter. So, they will have slender wings, means not very high chord, very long wings. So, go and search on this on internet and you will get some good information. So, this is what the whole story is. That is why you want it to be like that. You want very long span wings, because it will be like a 2D system. You will have very least amount of induced drag. So, your power required is very low, and you have extremely good glide ratio. So, once you have gained enough height, you just gently keep gliding throughout the night, and then wait for sun to come up, and then you can again start climbing up. That is the whole idea. So, this is a very simple principle how your solar powered UAVs work. So, it is not like that, I mean, they will keep flying. So, yeah, I mean, if you come down too much, you will use some energy to maybe maintain your height, do a level flight, and do station keeping basically. That is the idea. Okay. So, with that diagram now, we can sort of try to calculate this. Again, now I am not giving you the full derivation of this, because this requires a lot of aerodynamic theory which you do not need to know and is not relevant for you also. Okay. But I am just explaining briefly. So, what we are saying is that the induced drag is coming because of my tilting back of my lift vector, and the tilting back is happening by this angle, where my alpha I is my induced angle of attack due to the tip vortex. So, that is the angle, and with that I can approximate my drag as L alpha I, because sin alpha I and alpha I will be same, angle is going to be very small, maybe 1 degree, half degree, 2 degrees like that. Okay. So, for small angles we can easily apply small angle assumption. And now here I am going to introduce something which I unfortunately I will not have time to really go into the depth of it. If you want to understand and read this more, you can go and look at any good book on aerodynamics. So, for our course we have given reference of Introduction to Flight, that also has some details, but if you want to get further details, you can look at Anderson's book on aerodynamics or any other good book on aerodynamics. So, that will explain you this elliptical distribution and your lift inline theory and all underlying assumptions and everything you can learn from that, but that is not critical for a UAV engineer. I do not need to really go into the mathematical and theoretical aspects. So, that is why I have sort of skipped that detail actually. So, that is why I mean those of you who will do aerodynamics 1, they would get to learn about this in more detail. Right. So, what we are trying to do here is that I mean we are trying to find an expression for this induced drag, and the simple way of doing it is that actually using this elliptical lift distribution. So, according to this lift inline theory, if my wing profile is elliptical in shape, my lift distribution on that also is elliptical. Okay. And for that kind of case, I can find out this induced angle of attack as a function of my lift. So, like I said, I mean if you want to look at the derivation, you can go and refer to any good book on aerodynamics. Okay. They will all explain this. So, we get this expression for your induced angle of attack. So, this is now function of my lift, and of course, pi is your normal 3.1415926 or any approximation of that, and then this is new term which we already have looked at is the aspect ratio, right. So, normally we use this symbol aspect ratio. Okay. So, it comes out to be like this, okay. And what is my aspect ratio? B square by S, okay. That is a more general formula, and if my wing is rectangular then S is B into C. So, it becomes B by C. Okay. So, where B is my wingspan and S is my wing area. Okay. So, irrespective of whatever my wing shape is, this formula is the right way to calculate your aspect ratio. So, that is my aspect ratio. So, now with this alpha I can immediately calculate L into alpha I. So, I get this, right, as my induced drag value, where Q infinity is my same dynamic pressure, right. Q infinity is half rho V infinity square. Okay. So, now this I can convert back into my drag coefficient, which I will call as induced drag coefficient now, C d I, and that actually is C L square by pi A r. But this expression is only valid for elliptic planforms having elliptic lift distributions. But then in real world you will not have elliptic planforms, and therefore, you will not have exactly elliptic distributions. So, there is a small correction that we make, and we induce this or rather introduce this new parameter called the span factor or span efficiency factor or Ostwald's efficiency factor. So, this is efficiency factor. Okay. So, my CDI is equals to CL square by pi E into aspect ratio. So, AR is combined aspect ratio, right. Okay. Okay. And for elliptic wings, means having planform in the shape of an ellipse, it will be 1, otherwise it is less than 1, and typical value is 0.9 to 0.95. Okay. This can be estimated, or you can assume something based on your literature and other things, okay, for your approximate calculations like using this formula. So, with this now my total drag calculation is complete, okay. And you will not believe, I mean, this is actually the most important part. Getting the lift part is always easy, getting the drag accurately is the more difficult part. Even if I do use numerical tools like computational fluid dynamics, where I carry out CFD calculations using some sophisticated I mean algorithms and everything, and in that if you are not very careful, you will see that I mean matching the drag is difficult, matching lift is very easy, matching drag is far more difficult. So, that is what I mean we have done here. We have now total value of drag obtained analytically, of course, where I have profile drag, which consists of my pressure drag and my skin friction drag, okay, and induced drag, which is induced by lift, which also tells me now one thing: if my wing is put at an angle where it has 0 lift, then what drag we have? This profile drag. Okay. So, therefore, profile drag is also called as 0 lift drag, and that is why this coefficient name is CD 0, that is why we call it CD 0. Okay. So, this is drag without lift or drag at 0 lift condition, at 0 lift condition, right. Okay. So, this I can actually plot as a function of lift, and that graph is called a drag polar. Okay, so I skipped that part. Okay, yeah. So, this is like a drag polar. Okay. So, this plot of CL versus CD is called a drag polar, okay, which is basically just this representation of this equation in this kind of form. So, once you have obtained something like this, I can easily plot my CL by CD versus alpha, I can plot other things, and all this actually is important because eventually want my UAV to operate under optimal conditions. So, let me go back to this other two graphs, which will hopefully give us some clue about that. So, here I actually have put these graphs taken from XFLR or your Xfoil kind of software. So, there are these panel method based softwares which actually can compute your CL versus alpha, CD versus alpha very easily and quickly for I would say moderate Reynolds number. They are not very accurate for high Reynolds number and they are not very accurate for very low Reynolds number either. For moderate Reynolds number they are okay, they will give you reasonable answers. So, with that I mean I have gotten something and I am showing you comparison of 4 different airfoils. In this one is your NACA series. So, NACA 0010. So, what does this mean is basically the first 2 digit actually tells you the camber, okay, how much camber it has, and so it actually tells you the percent camber and the location of the max camber, okay, because that will determine your shape of the airfoil. And the remaining 2 terms, last 2 terms are actually these give you the thickness. So, 10 means it is 10% thick. Okay. So, if I look at say NACA 0012, which means it is 12% thick. Okay. So, this gives you the value of camber and this would give you the location of max camber in terms of percent of chord. Even here is 12% thickness is of chord, okay, 12% of your chord length. Okay. Right. So, that is not very important here. I mean nomenclature is fine just for you to understand, I mean like how they gave name, that is only true for NACA. So, they have 4 digit series, 5 digit series, 6 digit series, and then there are airfoils developed by individuals, companies, private companies. So, they may have named it in whichever way you want, okay. So, it does not matter. Okay. So, the key thing to understand is that I mean they have very different profiles you can see. So, this guy has S1223, it is giving me crazy high values of lift even at a very moderate and small angle of attack, 3 degrees it is giving me 1.5 CL max, right, while other guys actually are taking more time to build up the lift. So, this blue and black guy, so black is HD 7062 and blue is AG 36, these are actually giving me higher values of lift. It is still not high enough, I mean compared to my S1223, it is only reaching say 1.2 or so and that too at 6 or 8 degrees, right. But just looking at lift is not good enough, I need to see what is my drag, and I see that well green line seems to have actually consistently higher drag also, my CD is high everywhere. Yeah, so, you see while my blue line has lower drag, red line has lower drag at some places. So, red is my symmetric airfoil. So, this is confusing, right. Okay. I cannot say for sure which is better actually. So, what should I do? I should look at L by D versus alpha, okay. That is going to give me slightly better understanding and I do that. So, here it is actually. So, I have now CL by CD versus angle of attack, okay. And this gives me slightly better picture that oh okay, look my L by D is very similar for this blue line and green line. Blue line is AG 36 and green line is S1223, and interestingly my max CL max for this green line is coming approximately close to 2 degrees, while my blue line has a max or at around 4 degrees. So, how do I use this information? Let us say if I do not have to worry about anything else and I see okay, yeah, both of them have very similar performance. So, but yeah I mean similar, but there is still some difference. What difference can you see?
We can say the blue one is a bit better or more stable for us.
Better, why better?
Because we can have it at a greater angle.
Okay, greater angle, but beyond that also what you can see is that it has actually slightly flatter behavior from 2 to almost 6 degrees, yeah. Right. It does not show dramatic variation, which means I can operate at a range of angles of attack. What does it mean? Operating a different range of angles of attack. If I go to different angle of attack, it will change my what? See, it will change my lift, it will change my drag also, right. And changing my lift means I can change my speed. Okay. See, same UAV, if I am trying to design a loitering ammunition UAV, very popular these days, right. It is the most talked about happening UAV. Everybody wants to make loitering ammunitions, which are basically fixed wing UAVs which will go to longer ranges. Loiter means they can go and keep flying in that area for long periods of time, and then once the time is right and you have identified your target, they will go and take care of the target, right. So, these UAVs, I mean, if I am operating them, I would want them to reach the target quickly enough. Okay. So, once I go there, so I will like to travel at a faster speed. So, if I am traveling faster, I would prefer to operate, or my UAV would operate at a lower angle of attack or a higher angle of attack. Let us try to understand which one would be the case. So, my lift should be equal to what for my UAV to do a steady level flight? Weight, right, should be weight, right. I mean, if I draw a free body diagram of my airplane, yeah, let us say this is my airplane from the front view, yeah, and this is the lift acting on it, it must balance my weight, right, to ensure that it is maintaining level flight. Now, so this lift is equal to weight, but it is also now equal to my half rho square S into CL, right, and my CL is I can write this as CL alpha into some alpha. Okay. How? Because most of these graphs will have some amount of linear portion, and I can approximate that with this linear portion, okay. That for small angles of attack it will be like that. Okay. So you can see this, okay, this is not the correct graph, this, yeah, you see this is fairly linear, this is fairly linear, although this area is non-linear, remember that, okay, maximum lift area, and this also has a fairly linear profile, this also has a fairly linear profile. So, I will take that as a CL alpha into alpha. So, I will get the slope of this graph. So, I can write it like that, right. Okay. So, now from this I can see my angle of attack required, okay, to fly, or I can keep it like this, maybe I can keep this alpha v infinity square equals to twice of W by rho S CL alpha, right, which means for this value to be obtained, okay, if I increase this, I will have to decrease this guy, right, which means if I want to reach my destination quickly, I would like to fly at my relatively higher speed, the best speed I can fly at without compromising my L by D too much. Okay. So, maybe I will fly at best range speed, so that I can get there with minimum expenditure of energy and fastest. It is not like I will try to go like supersonic and go super duper fast, because then I will burn all the energy, I will not have enough energy left after reaching there. So, I will go to a speed which will give me best performance in terms of best range. So, we will come to those things in detail. So, I will select some speed which will be on the slightly higher side. Okay. So, then if I fly at higher speed, I will automatically operate at lower angle of attack, but once I reach there, I now have to kill time. Before I do my final mission, I have to wait and hang around and see where my target is. Okay. So, for that what do I do? I would want to fly at a speed which will conserve my energy, so that I can spend most amount of time there, maximum amount of time there. So, all that actually gets answered. So, now I will go to a speed which will be probably lower speed, okay, to decrease my drag and power consumption, okay. So, which means I will probably operate at slightly higher angle of attack. So, now you can see, so I can easily have one point of operation around here, another point of operation around here, and in both cases I have similar L by D, but I have different lifts or different lift coefficients rather actually. Okay. So, my lift coefficient would be different, because I will be operating at different angles of attack, but the good part is that my L by D would remain at least 40 all the time, okay, which is a good thing, right. So, I can maximize it at here when I want to go straight, in the sense of going towards the target. So, I may operate here which will be probably 50 or so, or 45 or 48, and then once I go back to loiter, I will operate probably at this high angle of attack, which will ensure lower speed, but I still have reasonably high L by D. Okay. But actually when I want to minimize my power, there is a different requirement, and we will look at that in coming lectures. Okay. So, this is one part of the part, okay, that is how I mean I will interpret my L by D graphs. Okay. So, this is one kind of interpretation. So, clearly blue and green look better, blue looks better in a certain manner, black has lower values, and I can see that I am going to get similar level of performance, not even same, it is still less. I have to operate at much higher angles of attack, okay. And higher angles of attack is not a necessarily good thing, because normally at higher angle of attack you will also have slightly higher drag. Why? Because your body is like this. So, you are exposing more area to airflow in a very layman's manner, one can understand that. Okay. But this may not be enough in all cases. I may also have to look at the third graph, or rather the fourth graph in this case. So, I looked at CL versus alpha, CD versus alpha, CL by CD versus alpha, and now we are looking at the pitching moment versus alpha. Okay. So, I hope all of you got the idea regarding CL by CD. Okay. So, the idea is that I mean I should have maximum lift and minimum drag, okay, and that is why I look at the ratio. I may have a different point where I may have maximum lift, but that point may have also high drag. Okay. So, I have to find a point where I have reasonable lift, but low drag. So, that my ratio is maximized, which is more important to me than just lift alone and drag alone. Okay. Fine. All right. So, now what is the deal with the pitching moment? How does this impacts or influences my UAV's performance? Okay. So, if I look at a normal UAV, let us draw maybe a aircraft. Okay. So, that is my fixed wing UAV, okay. And I have some lift coming from here from the wing, let us say, there will be some lift coming from the tail. Okay. So, what is the role of this CM? Well, we will not go into stability right now, we will just worry. Yes, it does affect the stability, how the CM changes, but we are not worried about that. We are saying I mean my craft is either stable or anyhow I have an autopilot. So, even if my craft is slightly unstable, I can make it stable by using my autopilot, okay, which is giving me some additional damping to make it more stable. Okay. So, it is a stable airplane, but what role does my pitch moment of a airfoil play for the overall airplane's equilibrium? So, for aerial vehicle we use, instead of calling it equilibrium, we have a more fancy term called trim. What do we call it? Trim. Helicopter, aircraft, whatever, any aerial vehicle we normally call it as a trim. So, what is this pitching moment actually doing? So, this wing is generating this lift, but it also generates this negative pitching moment. Negative pitching moment means it will try to bring the nose up or down. Negative is up, no, it is down. Okay. Your convention is that your nose up motion is considered positive, okay, which is if I look at clockwise direction we will consider positive, anti-clockwise we will consider negative. So, you see except this red line everybody else has strong negative moments and green has super negative moments actually, right, which means it is going to produce this thing which is trying to bring the nose down. Okay. How do I compensate for that? That is why you have your horizontal tail. Okay. So, in a conventional configuration I have this tail at the back, horizontal tail, and by deflecting my control surfaces there I can generate a counter moment which would balance this, right, or I can generate a lift which could probably be slightly downwards. So, this tail lift would be slightly downwards. So, I will actually set my tail plane in a manner that it is continuously generating some amount of small negative lift, okay, which will with the moment arm be able to cancel this nose down moment. So, if my pitch moment is high negative value, I would require a bigger tail or a smaller tail. Are you getting my question, guys at the back? What do you think? What kind of tail would be required?
Bigger tail.
Tell me.
Bigger tail.
See, you can think of simple equilibrium equation, right. So, you can think of a stick like this and I have some force which is my lift force acting here, okay, and at the same time there is a moment which is bringing it nose down. So, what do I do? If this is my CG, I have to of course apply some force. Well, CG would be probably closer to here, not quite here. So, I must apply some force which would actually balance this lift also and overall. So, if I do my moment balance, okay, actually there is a weight also acting, sorry, yeah. So, this need not actually have to balance entire weight, my bad, okay. It is actually only so this is my lift of the tail. So, lift of the tail plus my weight should be equal to my overall lift force, but there is a moment also acting. So, I will take maybe equilibrium about a moment equilibrium about this point. So, I have L into this distance say A minus this L t into this distance say B and plus this pitch moment. Yeah. So, pitch moment, right, this would go to 0, right. So, now to achieve this I can see that my L t would be equal to A L plus pitch moment divided by this B, right, simple equation. So, now you can clearly see that if my pitch moment is more, I would require more L t, yes. If my pitch moment is less, I can do away with a smaller tail also. I am just talking in a very simple sense where I am not worried about other things actually. There are other factors also which may govern this, but this is, I am sorry.
It would be constant. We will have to increase B to counter it.
No, it is not necessarily true actually. It is not necessarily true because I may have constrained over the dimension. I cannot make it unnecessarily long. Okay. I mean, I may want to do it for a particular mission where I have to fit it inside something. So, there are all kinds of constraints. So, user may say this UAV should fit inside a box, should fit inside a can, inside a canister, it should fit inside a particular truck and I should be able to carry so many of them in one truck. So, they will come back with all these requirements. So, you may have constraint that I cannot make it unnecessarily long. Yes, that is one option, that I can have small tail and a long boom, or a moderate tail and a moderate wing, moderate tail and the same boom. So, there are different options, but if I keep my boom length same, I am just trying to argue that okay, I can make wing my tail larger or smaller. Okay. So, what it boils down to is that having too much of high negative pitching moment is not good, and you can even consider tailless aerial vehicles. For example, you saw our biplane tail seater VTOL UAV, it does not have any tail. Okay. So, how do I compensate my this pitch moment? One option is I will choose an airfoil which like this symmetric airfoil which has almost 0 pitch moment, sorry, you see this, right. Okay. So, this has nearly 0. So, your symmetric airfoils, their pitch moment is almost close to 0 throughout, or otherwise also they will have very small pitch moment. So, then my compensation requirement is less. First of all, how do I compensate for this? So, in my biplane tail seater I have two sets of propellers, one set on the lower wing, one set on the upper wing. So, now to create this moment, my pitch moment, I have to basically operate my motor sets with differential thrust. So, one side will generate more thrust, other side will generate less thrust. So, if I have to encounter high pitch moment, my one side will always be working extra hard. So, it will have higher power consumption, it will be operating at a higher throttle value, higher RPM, and therefore, it may heat up, it may get burnt, or overall I mean you are spending lot of energy doing this thing which is not very useful. So, pitch moment also is an important factor in my design process, and along with L by D, high L by D, I would also want to have reasonable moments, not very high moments. So, this clearly now eliminates this green line. It says okay, this is actually almost 2.5 times my black line, which is HD 7062, and compared to blue it is almost 5 times higher pitch moment. So, this tells me this is not a good choice for me. So, this is how you would try to sort of interpret these lift drag tables for different airfoils, and this actually is an important aspect in UAV design, airfoil selection. All right, any questions on this? Okay, let us move forward. We talked about changing speed of my aerial vehicle, right, and by changing speed I can force my UAV to operate at different angles of attack and therefore, at different L by D conditions, and different L by D. So, I mean to enforce this I would eventually have to have my autopilot capable of commanding different speeds from the aerial vehicle. Now, how can I change the speed for an aerial vehicle? By changing thrust. So, I want to make it go faster, I will make my propeller go faster. Why? Because higher the speed, higher the drag. So, I have to overcome that drag. So, again if you look at my airplane aerial vehicle cartoon, okay, so I will have a propeller here, and so I have some drag force here. So, this propeller must generate some thrust to overcome my drag, and this drag is function of my velocity half rho V infinity square C D S, and this C D, even if it is constant or increasing with your angle or whatever, overall at higher speeds my drag will increase. So, my autopilot should be able to command the right amount of thrust to take it to higher velocity and be able to maintain that, which means I must have a sensor which should measure my airspeed, and that is what I mean this is about. This is the same technique which is used on a manned aerial vehicle, and that technique is basically use of a pitot static tube. Pitot static tube. What is this pitot static tube? So, this is a picture of that, and in this you can see there are 2 orifices. So, this is like a tube, concentric tube. I can even have just one tube also. So, nowadays I mean on smaller UAVs you will find a simple normal tube just like this. So, you will have a tube like this. This tube will measure your total pressure or also called as stagnation pressure. So, you may be, some of you may be familiar with Bernoulli's equation. So, that is basically your energy conservation, that is your pressure energy plus your potential energy plus your kinetic energy of a fluid system should be constant. So, the same idea is here actually. Here we will not worry so much about my potential energy and all, we will only worry about pressure energy and kinetic energy. So, total energy in the incoming flow is my pressure plus your dynamic, static part plus dynamic part, static pressure plus dynamic pressure, and that total pressure is getting measured by this main central orifice. So, this thing will be connected to a maybe a manometer, or nowadays you have digital pressure sensors, which will sense the pressure in this. Now, in addition to this I also need to measure the static pressure in the flow separately. So, that because here I am getting this is measuring the total pressure, static plus dynamic. So, I can either have another opening. So, lot of these sensors they would have a tube which will measure the total pressure, and this kind of boom based tube with a hole, and beyond that I mean they may have on their own sensor another separate port where they will measure the static pressure, because they are assuming that whatever pressure is there in the atmosphere, same kind of pressure would be felt inside the UAV this sensor body also. Otherwise, other way is that I can have a tube where there is a second orifice on the side of the tube, which will go through. So, there will be two tubes going actually, one at the center which measures the total pressure, which is this, and other on the side which measures this separately. Okay. So, with this I have now this information and this information measured separately. So, what do? I simply use this equation and I can write this as half rho V 1 square equals to P naught minus P. Okay. And I am able to measure these two parameters. So, your digital sensors would measure this actually in the form of some voltage, and then there is some factor which will you multiply with that is a calibrated sensor, and with that it will give you a pressure reading. So, it will give you this differential pressure reading, which gives me my dynamic pressure. So, now I can, so this is getting computed in my small electronic device which is there, and this will be talking to my autopilot. So, autopilot will get this information from there, and using this now I can compute this V 1 using this formula, which is twice P naught minus P divided by this rho and then square root of that. So, this way I can now estimate my air speed. Note that this is not my ground speed of the UAV, it is the air speed of the UAV, and for a fixed wing aerial vehicle air speed is very important. It is important for rotary wings also. Why, that will come later, but it is important. Okay. So, actually every UAV must have a pressure sensor or this pitot tube basically, even a rotary UAV should have this. Otherwise, I mean you will end up pushing it in a domain where it will be trying to fly in extremely high wind condition, maybe a headwind, and it may end up saturating its actuators, which can result in crashes. Okay. So, it is better to understand this. There are some indirect ways by which also now UAVs are able to estimate wind speed, purely based on the tilt they have in hovering flight, but that is a very crude way. I can actually easily put a pitot sensor, and I can align with the wind and then get a good estimate of how much my wind speed is actually, right. Okay, so, but now there is a catch here. P naught and P I am able to measure. What do I do with my rho? Rho is my density. Okay. What do I do with this? How do I get this? So, that is where I mean we have two approaches. Okay. One approach is that maybe I have a lookup table for my rho, or there is some atmosphere formula based rho calculation. So, I somehow calculate this density by using my standard international atmosphere charts or formulas which are used to populate those charts, and I somehow estimate this based on my altitude of operation, my ambient temperature, and I use the true density prevalent in that condition. Then if I can do that actually somehow, then I will call that as a true airspeed, but it is a tricky thing, especially with small UAVs you will never ever do this actually. Even for manned aerial vehicles normally you do not have this, because it is almost impossible to know all these things very accurately and be able to estimate my density in real time with high degree of confidence. So, they do it they keep it simple. Keeping it simple means I will actually use a fixed density all the time, and what could be that? That could be my sea level density, which is my standard value. So, my rho s I would keep, this is sea level density, and the value for that normally you would take is 1.225 kilograms per meter cube, and if I use this in calculating my airspeed, then that becomes my equivalent or indicated airspeed, and that is what we work with actually. We will rarely ever actually get the true airspeed, we will always get this. Yes, so true airspeed and your equivalent airspeed are same if you are flying at sea level or close to conditions which are similar to sea level. But if you are flying it at a higher altitude, you are flying it at 4000 meters altitude or 6000 meters altitude, it would not be same. But this still serves the purpose. Why? Because I know my relative change in speed with fair accuracy when it changes up and down. And another factor is that from my true airspeed and my indicated or equivalent airspeed, which one is do you expect to be higher? So, question is that my this V1, which is I will say true based on this ambient density, this is going to be higher or this is indicated airspeed, this is going to be higher. Note which one is higher, this rho s is more or this rho is more. So, rho s is greater than my rho, that is how it will be always. The moment you start climbing, I mean as long as we are not going in stratospheric environment, I mean anywhere else also, I mean it will be rarefied atmosphere. So, the moment I go above sea level, it is always going to decrease. Okay. So, this is always the case, which means this guy is more. So, my Vi V1 with this IAS will be less. So, my IAS indicated airspeed is always less than true speed, and this actually is a good thing. Why? Primarily because the reason why I need to know my airspeed, see I can also estimate my ground speed. How? No, I am talking about ground speed. My UAV speed with respect to earth, how do I get that? GPS, not IMU, GPS, right. So, or GNSS to be more precise. So, every UAV is getting navigated through a INS plus a GPS or GNSS system, right. So, your GNSS system is doing the localization and positioning, and the rate of change of position will give you the speed. That is the same thing which you see on your Google Maps, right. If you are using for your navigation and you are sitting in a car, it will approximately tell you the car speed with a small lag. So, same thing I mean you can do with your UAV also. So, your UAV's ground speed is also available to you, but for a fixed wing UAV in particular I do not care about that so much. What I care about is my airspeed. Why?
So the driving factor of lift and
Right, because my airspeed determines my lift and drag values, and if my lift comes below my weight, my airplane will stall, means it is no longer able to support its weight, it will start descending, falling, whatever. So, I must actually maintain my airspeed above my stalling speed, right. So, what I am saying is that should be greater than, okay. Now, my sensor here is actually giving me my indicated airspeed. Okay. So, if I ensure that my IAS is more than my stall speed, does it ensure that my true airspeed is also higher? Yes, because we have another relation here, right. My TS is actually more than IAS. So, there is some margin for you that you are always safe and you will never come close to that. So, that is why I mean this is good enough for me. I need not really worry about, or if there is a provision, I mean if there could be more sophisticated sensor which actually can give you a better estimate, which is fine. I mean if that is the case, I mean you can use that, it is not a big deal. But even if I do not do that and I use only this sea level based thing, I am safe. I would not have my aircraft stalling and falling from the sky, right. So, that is the whole business about this measurement of airspeed. Okay.
So, can we use any anemometer kind of thing to measure the airspeed, like a rotary kind of thing?
No, those are not very accurate. Okay. This is the most accurate thing.
Okay.
Those are fine, I mean, but they are not that accurate. Because
if that is the case, then we do not have to calculate the density and all, we can directly get the speed, right? I mean,
No, but that also actually depends on density. You will not get directly speed, right? Because those are mostly drag based. Right? So you have a rotary thing which is actually a small
exactly, proper.
hemispherical cup, right? So it's actually like your Savonius wind turbine. Yeah. So it's like a small wind turbine, and this wind turbine is based on drag. So this RPM is a function of your density. So you are not escaping that actually. Okay. So whatever calibration is giving you, it only knows the RPM, but your RPM is a function of your density on your drag, right? Okay. So it's not free from this problem. This is the most accurate thing, very reliable, solid. And sometimes I mean bigger UAVs would actually have more than one, okay, to get a more accurate estimate, okay, to get these things. Okay. And also in case I mean something happens, it gets damaged or clogged or something because of conditions, because if you are operating at very high altitude conditions where I mean the freezing may happen, I mean some snow deposition can happen, then I mean you may have to make this heated also, so that I mean there is no deposition of ice or snow or some such thing, okay, which will block the flow and start giving you wrong data, okay, because see all sensors are fallible. Every sensor has limitation, and if there is a limitation, I have to have redundancy for that. I have to have another sensor which will back it up, otherwise I mean I am just purely dependent on that, and that is the story of your Boeing Max, right. The so many Boeings that crashed, they had issue with this angle of attack sensor, and they did not give enough redundancy for that, and the sensor gave wrong data, and the autopilot thought that okay, airplane is actually climbing at very steep angles. So it commanded the whole airplane to go nose down, and by the time the pilot realized that, it was too late, because if it goes in a steep dive, it cannot come out of that. So that is another important aspect. I mean, so this is system aspect. Okay, so I will just take this one couple of minutes and finish on this. So this is as such instrument panel which is there on a typically an airplane, but how it is relevant for a UAV? Is it relevant or not relevant? Why? How?
In a ground station we can have
Exactly. So now for a manned aerial vehicle, I mean you have all these instrument panels on the craft. Now all these panels, virtual panels would be there on your computer on the ground, okay, but they are still the same. They would look very similar, and their behavior is also very similar. They are virtual sensors, but they will actually indicate the same things which normally a pilot would actually see when he is flying a manned aerial vehicle. Okay. So let us look at them quickly. So the most important and critical sensor or rather critical instrument or indicator is this. What is the name of this? No, it is not altimeter. This is called artificial horizon. Okay. And the hint is there, right? I mean you have blues which indicates sky, and you have browns indicates ground, which means when your UAV is operating, you will get telemetered data on your GCS, ground control station. GCS is ground control station. Okay. So you will be seeing this continuously. So this actually tells you the pitch angle of the craft, and to some extent it may give you some heading also, because this is also there, and these gradations are there. These gradations will tell you the attitude, pitch attitude directly, which means 10 means. So one thing is that I mean if I see more blue, so you see I mean ideally you would want this blue and brown to be balanced, half blue half brown, which means you are at level, absolutely level, you are neither climbing nor descending, and these instruments are there for every UAV, fixed wing, rotary wing, every type of UAV. So I want this blue and brown to be equal, but the moment I see more blue, what would it mean? You are climbing upwards. Okay. So, it goes to 10 means 10 degrees, 20 degrees, 30 degrees. If I see more of brown, which means I am descending, okay. So, I am looking the ground. So, this is actually a visual feedback for a pilot or the operator of the UAV for that matter here, and he can immediately take some action if he is manually controlling it, or if he sees some anomaly, he can try to do certain things to interfere with that and try to balance things out. So, this is one artificial horizon. Then other important parameter is your airspeed indicator. Now, you will see airspeed indicator mostly either in the dial gauge form or it could be a numerical display on your screen. Also, these gauges are old things. Now, modern aerial vehicles, even manned aerial vehicles do not have these gauges, but they still get represented on your LCD panel or what is called as multifunction displays. So, now aerial vehicles which has only this multifunction displays and no old gauges, they are called glass cockpit. So, all modern airplanes will have only glass cockpit. Does not mean it is made of glass, it simply means that your electronic displays are made of glass. So, even in our GCS on a laptop you will see this kind of gauges being created actually, because people are used to of that, and these instrument panels have been created because intuitively you know okay what is happening. So, that is easy to interpret. So, this is your airspeed indicator, and here it shows knots conventionally, but you can get it in meter per second, kilometer per hour. I think in electronic displays you can switch units and all easily, no problem. I think its time is also up, so we will stop now, and we will continue from here in the next class.